So welcome to the first problem solving session in this course, Fundamental Algorithms, Design and Analysis. So if you have any questions, you can unmute yourself, but if you do not have any questions, then please keep yourself muted. That will help us in the discussion. So the idea in these problem solving sessions is that we will look at some sample problems, and these problems are going to be helpful for you to attempt the quizzes and in your exam. So in the first week of lectures, we have seen different sorting techniques and some basics elementary algorithms. So we are going to look at some problems based on the videos that we have seen in the week one. Right, so let's start with the first question. So this is question number one. So here we are asking, what is the space complexity of merge sort? So we have seen a sorting algorithm called merge sort, and we are asking that how much space does this algorithm take? And when we ask about space, we ask space in terms of the input. So n here is the input size. So you can think of it as the number of numbers that are given to us for sorting. OK. So what is smart sort? So how does smart sort work? You have seen the videos, I believe. So let us take a few numbers and then we will apply smart sort on that. OK. Let us say we are given these numbers to be sorted. So here n is equal to 4. And we want these numbers to be sorted using merge sort. So we want to apply the merge sort algorithm. Who has unmuted himself or herself? OK. So have you seen the merge sort recurrence? Any of you? So how can we write the running time? So Tn refers to running time of the algorithm when the input size is n. And let us say Sn refers to this space complexity, that is space required for an input of size n. So we know that in merge sort we divide the input in two parts, two equal parts. So there are two subproblems of size n by 2. So the running time is 2 times t n by 2 because we will again apply merge sort on these two subproblems of half the size. And then we will march the solutions to these two subproblems. That will take additional time, right? If you have unmuted yourself, please mute yourself. Whoever has unmuted himself or herself. OK. So the time required to march the solution is something we have to write here. So anybody knows how much time is required to march the solutions to these two subproblems? So what do we do in march-sort? So let's run march-sort on these four
So this
numbers.
would require an effort, a linear effort, say effort of the order of n here.
Right, right. That is correct. So that the reason is that once we have applied march-sort on the two subproblems, then we have already obtained two sorted lists and want to march two sorted lists. So this is a sorted list, let us say. So what will happen? Let us say we are going to use this example only. So in this case, one sorted list will be 27 and 38. The other sorted list will be also. So we are sorting in ascending order. The 43 will come after 10. So how we march is we make comparisons between the smallest element in the one subproblem, one sub-solution, and the smallest element in the other sub-solution, and we compare that which one is smaller. Whichever is smaller, we put it into a new array. So which is our output array. We have an output array. So in this case, 10 and 27 is sorted, compared. So 10 turns out to be smaller. So we push 10 into the, I mean, push in the sense we put 10 from this right sub-solution to the result. So this is a result array, which we are going to output. And then we will compare the smallest element in the remaining sub-solution with the smallest element in the remaining sub-solution. So 27 turns out to be smaller than 43. So we will take 27 from the left sub-solution. And then we will be left with this. Then we will take 38 because 38 is smaller than 43. And then we are left with 43. There is nothing to compare. Okay. So this is assuming that March sort has correctly worked and it has given us the sorted lists to those two subproblems. Okay. So that is the reason how we require order n time. So n by 2 was the size of the array here and n by 2 was the size of the array here. And we have made comparisons. How many comparisons? At most n, or rather n minus 1, because one element, the last element, which we did not have to compare. So that is the reason order n time will be required for merging the two sub-solutions. So this is the running time recurrence for merge sort. Okay, so this was just for warm up. So we want to ask ourselves that what is the space requirement? What is the space complexity of merge sort? Okay, so similarly, we have to argue that, okay, how much space will be consumed by the algorithm? So you have to see how the algorithm works, and it also depends on implementation of your algorithm. So one implementation can take more space than the other. Okay, so when we are asking space complexity, so we are asking that if we do the best job, if we have the best implementation, then how much space will be required? Okay. Space in the sense additional space. So that is given to you. So that is taken n space, order n space. Now, additionally, how much space will be required? That is the question. Okay. So for ease of analysis, let me write down a small pseudocode of mod sort. Or rather, instead of pseudocode, maybe one example will help us answer this question. Pseudocode can get slightly complicated. So let's do one thing. So let's take this example only, and then we will argue with respect to this example. So here n is equal to 4. So there are 4 elements. So we have a result array, so which we are outputting, that is there. So the result array is of equal size. There is a result array. This result array is additional. So of course, n elements will require order n space. And how the algorithm has proceeded is that it has divided the array into 2 equal parts. For ease of calculation, we will assume that the size of the array is even. So n is even. So we are able to divide the array into 2 equal parts. If n is odd, then we will not be able to do it, but we will not go into that complication for the sake of simplicity. So now once we have divided the array into two parts, then we call mod sort upon the two parts again. Then that recursive call to mod sort will divide the array further into two equal parts. But once this division is done, then in each part, only one element is left. And then we're asking that what is the sorted order of one element? So the sorted order of one element is that element itself, right? There is nothing to compare. So the mod sort will keep on calling itself recursively and dividing into smaller and smaller subproblems till a subproblem of size 1 is hit. That means one element is remaining in the subproblem. Okay. So how many times, if there are n elements in the array, then at most how many times will the merge sort will call itself recursively? So that is the question we should ask ourselves.
Log n times.
That is correct. Why is it log n?
Because we keep on dividing things into two halves, so this will lead to a. So let us assume that upon reaching to a depth of say k, we find a value such that 2 raised to the power k becomes equals to n. So then k
Right,
becomes equals to log n.
that is correct. Since each time the subproblem size is halved, so after k calls to itself, that means after k recursive calls, the subproblem size will be how much? So we started with n. So after k calls, this remaining subproblem will have size n by 2 to the k. After one call, size is n by 2. After second call, size is n by 2 square. After third call, size is 2 n by 2 cube, like that. So after k calls, size of the problem remaining is n by 2 to the k, and we stop when the size of the problem becomes 1. That means only one element in the array is left. So at that point, what is the value of k? So that many iterations we will do. So at that point, we have this equation satisfied that n by 2 to the power k is equal to 1. That is the problem size. So that means we can simplify in the following way. So this gives us that k is log to the base 2n. Fine. So these many recursion levels are there. So now we have to dig deep into that what happens in each recursion level in terms of space. Okay. So at the base level, that means when subproblem size is 1, we simply return the element. Okay. So for example, when we divide this two size subproblem further, then we have further division of this subproblem into two parts. Then this subproblem, once we call mod sort on this subproblem, then 38 is returned, and then 27 is returned from the other side. And then we have maybe one array of size 1 here, one array of size 1 here, and then we will do the comparison as we have seen. So 38 and 27 will be compared, and then we will be obtaining this array 27 followed by 38. Similar thing happens here. So this returns 43, this returns 10, and then comparison takes place. and then we obtain a sorted order, n followed by 43. And then finally we get our result array, which has 4 elements by comparing these two ends. Okay. So if we are naive, if we are saying that, okay, in each iteration, we are going to have a result array of size equal to the size of the subproblem, isn't it? So when the size of the subproblem is 1, we have a result array of size 1. When the size of the subproblem is 2, then we have a result array of size 2. And so on. Then if we're naive, then what is the space complexity? Then S of n will be sum of, so how many subproblems of size 1? N subproblems of size 1 and n by 2 subproblems of size 2, n by 2 to the k subproblems of size k, and finally there is one subproblem of size n. So that much space will be good, isn't it? So that is like we're counting that what is the size of the array that we are outputting. So at every call of the mod sort, we are outputting something. So this is expected. Okay. Now, this definitely is not the best of things we can do. The question is, what is the space complexity of mod sort if we do the best implementation? Okay. So we have to think that what we can do. I mean, what modification we can do to the implementation such that this much space won't be required. Can you do some reusing kind of thing? I'll give you a minute to think about it.
So can you please repeat the question? It is.
So we want to ask that what is the space complexity of mod sort when we are given n elements to be sorted? So this is a question.
Okay. So since we would be maintaining an auxiliary array here, so clearly we would be requiring additional space of the order of n here. Because whatever, I mean, the outcome of the merge procedure is getting stored in a separate array.
Yes. But this additionally, each subproblem is giving rise to an auxiliary array of the size equal to the subproblem.
Yes, and that can be reused. No, that cannot be reused because this is we are not doing things on the fly. So we are explicitly storing these values somewhere in an array. So we would be requiring an additional space of the order of n.
Why is it of the order of n? So this is the calculation I did. So this is the calculation counting the additional space that will be required. So consider the basic subproblems. That means those subproblems that contain one element each. How many such subproblems are there?
So having one element, so we would be having n number of such problems.
Correct, correct. So since there are n such problems, so each subproblem is outputting or requiring one auxiliary array of size 1, isn't it?
Yes.
So n into 1 space is required for such subproblems. Now consider size 2 subproblems. That means it's a problem like this.
Yes. But then same space can be reused also.
Right. It depends on the implementation. If the implementation is naive, then the same space, yeah, if you do not reuse the same space, then the amount of space you will end up using would be this expression that there are n by 2 subproblems of size 2, n by 2 to the k subproblems of size k, and so on. So one subproblem finally of size n, and for each subproblem, the additional space requirement is the size of the subproblem. But that is naive, and probably we will be able to see that this naive implementation can be improved by reusing the auxiliary space. And if we have the implementation that reuses the auxiliary space, then at any point, the size of the auxiliary space will not exceed n, because the array size itself is n. Right. So therefore, the answer to this question is order n. That is the best implementation will give us this complexity. Okay. Let's move to the next question. Or if you have any questions, you can ask me before we move to the next one.
So will it be the same in case if the array size is odd number?
Yeah, the odd number case is hello. Yeah,
Yes, sir.
the odd number case is a bit complicated. So here we will not be able to divide the array into two equal parts, but asymptotically it is going to be the same. Asymptotically in the sense means in order notation. So for example, let us take five numbers. So let us say instead of 4, we have five numbers: 38, 27, 43, 10, and I don't know, 18. Then we can decide whether we want to partition here or we want to partition here. So we can either have a 2, 3 subproblem, or we can have a subproblem of size 3 and a subproblem of size 2. And then for this another odd size subproblem, we'll have this two different sizes of subproblem. But since the subproblem sizes only differ by 1, so size of adjacent subproblems differ by at most 1. So asymptotically, we will end up using order n space only. Does that make sense?
Yeah, thank you.
Okay, so if you have gone through the asymptotic notation video, then you will be able to understand this question. So this question is asking that how do you write this function? So this is a function of n. Okay, so let's call it Tn. So asymptotic means that in the long run, what does this function look like? That means if you make n large enough, then what is the uh, type of the I don't know
N
why
power
it
4.
is not.
N power 4. Second
Yes,
answer.
there is an echo. Okay, so why is it n power 4? Whoever is saying.
Probably the log n is normally less than n square always.
Oops, just a second, my battery is running out. Yes, that is correct. So the dominating term out of n to the power 4 and log n is n to the power 4. So we have seen that if there are two functions f of n and g of n, then the addition of these two functions will be order the larger of the two. So I will write it this way. Order max of fn comma gn. Okay. So it is easy to see that n to the power 4 is a polynomial whose degree is 4, whereas log n is very small. Log n is even like exponentially small than n. So log n cannot dominate n to the power 4. In fact, n to the power 4 is dominating term. So that is the reason order n to the power 4 is one of the correct answers. Is there any other correct option?
Maybe C.
Yes, C is also correct. C is also correct because. So what is the order big O notation? What is the definition of the big O notation? So if I say that some function f of n is big O of some function g of n, so what does that mean? So that means that g of n is at a high level, g of n is larger than f of n. Okay, so one can write that n is order n squared. So this is not a tight notation. We're just saying that look, n squared is generally bigger than n. Okay. So if you look at the definition of this function, this big O notation, it says that if there exists a constant c and some number integer n naught, which is sorry, yes, some integer n naught, such that for all n greater than n naught, f of n is smaller than g of n. That means f of n is at most this constant times g of n. Then we are going to conclude that f of n is actually order of g of n. So if gn is very large, like in this case, gn is n to the 4 times some more things, log n, then we'll be able to say comfortably that n to the power 4 is order n to the power 4 log n. That is fine. Or in this case, our function is n to the power 4 plus log n. So this we will be able to say that this is. Is this clear? If it is not clear, then you have to read the definition of big O, big omega, and big theta. What are these notations which we have seen in the videos? Okay. So shall I move to the next one?
Yes, sir.
Let's move to the next one. Again on asymptotic notation. This was question 2, so this is question 3. Let's call it 3. So if Fn is order Gn, this is big O. So if Fn is big O of Gn and Gn is big O of Fn, can we say that Fn is equal to Gn? So there we have two functions, Fn and Gn, and this information is given to you. So based on these two information, can we conclude that these two are in fact identical functions?
No, I think it's wrong.
Why is that?
Because if the order is same, it shall not be implies that the equation is same, the expression.
Okay, so let's
So it maybe it's a n square, it may be 2n square something.
Makes sense. Okay, so I don't know why Madhubalan is unmuting himself. I can hear myself again, so there is an echo. Are you using two devices?
No, I'm using only single device.
Okay. Okay, fine. Anyway, let's look at why this is false. So as Madhubalan has pointed out that this is false, and he is correct. And the reason is simple, that he has given an example also. If fn is n squared and gn is 2n squared, then this statement that fn is order gn is correct. Because look at this definition. So the definition of P is this. It should exist a constant. So in this case, what is the constant? That would let us conclude that f of n is order g of n for these two functions. So it takes the constant to be 4 or anything that is greater than 2. Then, okay, so this is even simpler. Take the constant to be 1 only. So fn, instead of fn, you have n squared, and then instead of gn, you have 2n squared. So n squared is always less than or equal to 2n squared. So clearly n squared is order 2n squared. But in the other direction, what is the constant we should take to prove this? So we have gn order of fn. So gn is what 2n squared. So you want to take a constant here such that that constant into n squared is more than 2n squared. So you can take any constant which is greater than 2. Let's say we take 3. So for that constant, we'll be able to say that this relationship holds that 2n squared is in fact order n squared. So both these things are correct, but n squared is clearly not equal to 2n squared. So fn is clearly not equal to gn. So that is the reason this is false. Is that clear? Okay, we'll move to the next one. So what is the worst case time complexity of quicksort? Any guesses? So you are sorting n numbers. Okay. Yes. So what does quicksort do? So you have n numbers. And these numbers are not sorted. So we want to output the sorted sequence of numbers. Let's take some examples. I don't know, let's say 40, 31, 4, 12, 35, 20, 26, 15, 34, 50, and I don't know. Let's say 6. So what Quicksort would do, it's going to pick a number and it's going to decide that in the sorted sequence, this number should lie. What is the position of that number? So, for example, if we consider this last number 6, so the first step is to decide that in the sorted sequence of this number, where should 6 lie? What should be the position of 6 in the sorted sequence of these numbers? How many numbers are there? Okay, there are 11 numbers. That is not a problem. So if we have the sorted sequence of these numbers, then 6 should lie where that it is going to decide. And moreover, so let us say 6 should lie here. It is also able to partition the rest of the numbers into two parts. One consisting of the numbers greater than 6 and the other consisting of the numbers smaller than 6. So in this case, only one number is smaller than 6. So it would be able to identify that 4 should lie to the left of 6 and rest of the numbers in some unsorted order, probably unsorted order, will be here, will be populated here. Okay, then it will apply quicksort once again on these two particles. So this partition is already taken care of because there is only one number here, but this partition needs to be solved again. So again, it will identify one pivot. So this element which is dividing the array into two parts is called a pivot. Okay, so that pivot, what does the pivot do? The pivot lets you divide the array into two parts. So again, there is a pivot. So that will divide the array into two parts. This is one part consisting of the numbers less than the pivot. And this is the other part consisting of the numbers greater than the pivot. So finally, when this process continues, finally what will happen? That we will be left with the sorted array. So that is what we have seen in the videos, that how quicksort has worked. Okay. So in the worst case, how much time this can take in terms of n? So let's ask ourselves that what about the first two options? Are these two options correct? Or one of them is correct?
No, not correct.
Correct. So for so there is a rule of thumb you can use it for sorting. As small as these two numbers, like log n and not n, are never going to work. Sorting will minimum take n log n time, unless you have made assumptions about the input and other things. In general, if you're sorting in numbers, you cannot do better than n log n running time. Okay, so we have immediately ruled out these two options. Now we have to check how about these two, which one is correct.
Worst case, big O of n square.
That's right. That is correct. So why is that? So the easiest way to see that is to write the recurrence of running time. So do you know what is the recurrence? That so let us say Tn is the worst case running time of quicksort on input size n, or rather n numbers, then what this pivoting is doing, it is dividing this array, this subproblem, or rather this problem of size n into two parts. So one part, let us say, has size k, then the other part would have size n minus k. And then it is again applying the same algorithm on these two parts. So what can happen in the worst case, this partitioning into two parts by the pivot can be very skewed. That means a lot of numbers, for example, in this case, it has happened. So only one number was smaller than the pivot and rest of the numbers were larger than the pivot. So the subproblems were not close in size. I mean, it is called a skewed partition. So unmuted himself. I would request you to keep yourself muted unless you are asking a question. Fine. So the problem with the skewed partition, that means a partition which is small on one side and very large on the other side, is that the recursion becomes something like this. So in this case, what has happened? One side we have a subproblem of size 1, and the other side we have a subproblem of size n minus 2. And another element is the pivot, right? So n minus 2 one side, 1 on the other side, and the pivot itself is another element. So n elements. And some, I don't know, constant. How much time is required to do the partitioning? Not constant. The time required to do the partitioning is order n. Okay. So if you solve this recurrence, every step you are incurring order n time, and there are this recurrence hits. I mean, this recurrence terminates when all t's become 1. So from n minus 2, the next problem becomes, let us say, n minus 3 and so on. So n minus 1 iterations, and each iteration you take order n time. So this is in each iteration, the cost of each iteration. And this is the number of iterations. So this is order n squared. Okay. So this is the problem. So now you give it a thought when you go back. I mean, when you meditate on this problem in your free time, then try to construct, let us say, 10 numbers for which the partitioning is going to be as skewed as possible every time. Okay. So this is a homework you can try to think about it. So that is the reason in the worst case, this will be your running time for quicksort. Is that clear? If you have any questions, you can unmute yourself and ask me. Okay, so we'll move on to the next one. So previous question was question number 4. Now we have question number 5. This is also on sorting. We have seen insertion sort. What is an insertion sort? Let's look at the insertion sort. So let's first read the question. So we have the following list of numbers to sort. And we apply insertion sort on this list of numbers. And the question is, out of these 4, which list represents the partially sorted list after 3 complete passes of insertion sort? So how insertion sort works is that it takes this input and refines it. So it runs iterations and it in each iteration, the input is transformed so that it goes towards the sorted sequence, which is our goal. Okay. So the input is the following: 15, 5, 4, 18, 12, 19, 14, 10, 8, and 20. So these numbers are to be sorted. And after first iteration, there is some intermediate state of this array. After second iteration, there is another intermediate state of this array. After third iteration, there's another intermediate state of this array. Right. After first, after second, after third. So the question is asking that after the third iteration, what should be the state of this? So finally the state of that is a sorted sequence. Finally, we would have the sorted sequence. Let's write it down. 4, 8, okay, 5 is here. 4, 5, 8. What is that? No, what is okay? After 8, what shall we have? 10. After 10, maybe 12. What's next? 14, 15, 18, 19, 20. That's all. Yeah, how many numbers are there? 5 and 5. 10 numbers are there. We also have 10 numbers. That's right. So this is the final. After all iterations of insertion sort are over. So after all iterations, this is what we have. The question is what happens after the third iteration?
C.
C. So after the third iteration, we have this. Why is that so?
At the first iteration, the 5 will come at the first position. And in the second iteration, 4 will come before 15. And the third iteration, 4 will come at the first position. And probably, so remaining will be in the same positions.
So why not A?
Because the last number 8 and 20, 10, it should not be sorted because the last
Okay.
questions.
Okay. So you're saying that. Because. Okay, so this should be the order. 8 is the problem. That's what you're saying.
Yeah.
Okay. Yeah, you should mute yourself, otherwise I'm hearing myself again. Okay, thank you. I don't know why is that happening. So let's understand what he said. Let's understand how insertion sort works. So insertion sort means that you're inserting something into something. Okay. So what happens is that in the insertion sort, in the first iteration, so we're looking at this unsorted list of numbers. So we're looking at this list. And in the first iteration, we are asking that where should the second element, rather, let me put it this way. So in the after the first iteration, we should have the first two elements of the input in sorted order. So to start with, before the first iteration, that means after the 0th iteration, the first element is already in sorted order. So if you forget, let us say we don't look at anything except the first element, then that element itself by itself is in sorted order, irrespective of what has come later. Okay. So we're not looking at the rest of the elements, we're looking at the first element. The first element by itself irrespective of what's in the rest of the world is in sorted order. Okay, that's right. Now, after the first iteration is done, then we'll focus on the first two elements and would like to see a sorted order among the first two elements. After the second iteration is done, insertion sort ensures that the first three elements among themselves are in sorted order. Okay. After the third iteration is done, insertion sort ensures that the first four elements are in sorted order among themselves. Okay. That is the property that the insertion sort maintains. That means after the n-1th iteration, all the elements will be in sorted order. That's how insertion sort works. Okay. So you have to worry about the first four elements only after third iteration. So what are the first four elements? 15, 5, 4, and 18. So we should have this order. 4, 5, 15, and 18. And rest of the things we don't have to worry about. Rest of the things remains as it is. That is the reason C is correct. Is that clear? So we have solved 5 questions so far. And this is a 2-hour session. So 1 hour is over. We'll have 5 more questions. But since this is a long session, I think people may need a break. So at this point, we'll take a small break, about 5 minutes, maximum 5 minutes, and then we'll be back after 5 minutes. Okay. Okay, so we'll start once again after 5 minutes. I mean, we are back. We'll start again now. Fine. So let's move to the next question. So this is also an insertion sort. This is a question. I will let you read the question. If you're not able to hear me at any point, please let me know. So there are numbers in an array which are all same, and you're applying insertion sort on this input array. So the question is, how much time will it take for the algorithm to terminate? Suppose this is already sorted, but the algorithm will still do its job. So algorithm will still perform the steps that it is supposed to perform. The question is, how much time will it take? So in the worst case, how much time insertion sort takes? That we haven't seen, but yeah, anyway. Yes. So the worst case time complexity of insertion sort is order n squared. So this is an easy example. This is an easy example. So we can expect at a high level, we can expect that if we don't do any calculations, that the time required would be somewhat less than order n squared. So this is definitely ruled out. This cannot happen. The worst case itself is order n squared. Then how can this happen? Isn't it? So this cannot happen. Order n squared is also unlikely because we have an easy example, right? So you have to select between this and this. So any guesses? B. Vishal is saying B. That is correct. So B is the correct answer. Why is that? So you have to understand how insertion sort works. So last question we have seen that insertion sort maintains after the ith iteration a property. That property is that I plus 1 elements, the first I plus 1 elements in the array among themselves should be sorted after the ith iteration. Okay. So how does insertion sort achieve this property? So let's work on this array only, this previous question only. So to start with 15 is already in sorted order by itself. The first element is already sorted by itself. So forget it. Now, the first iteration has to ensure that 5 and 15 are sorted. So after first iteration, this kind of thing should happen. So 5 and 15 should be swapping positions, and rest of the things will be as it is. Okay. So what it does is it makes a comparison. It makes a comparison between the element at hand, that means 5. First iteration works on the second element. So we have an element 5 at hand. So we have to decide that okay, 5, where should it be placed with respect to the elements to its left? So it does this swap, okay? And rest of the things are as it is here. Let me write it down for the sake of completeness. Now, in the second iteration, the element at hand is 4. Now the question is asking that okay, 4, where should it be with respect to the elements on its left? So it makes a comparison between 4 and 15. So it realizes that okay, 4 should not be to the right of 15. 4 should rather be to the left of 15 because 15 is higher than 4. So it makes this swap. But that is an intermediate swap. There is a loop inside. So 4 comes here, 15 is here, and then 4 is again compared with 5. And then it realizes that, okay, 4 is even smaller than 5. So 5 should also be swapped with 4. So now finally 4 comes to the first, followed by 5, followed by 15. So it achieves this property that the first 3 elements among themselves are sorted. The rest of the things are as it is. Okay. So now the element at hand for which we want to make decision is 18. So 18 gets compared to 15 and it says, okay, fine, 15 is smaller than me, so I don't need to do any swaps. But then there is a comparison, and it turns out that all comparisons sort of fail to produce a swap because 18 itself is kind of the largest among the 4. So this is what we get, and rest of the things are as it is. So when does a comparison? So when a comparison takes place, okay, so yeah, so we have to look more closely into what has just happened. So 18 compared itself with 15. Okay. 18 was the element at hand. It compared itself with 15 and it realizes that, oh, look, I am bigger than 15. 18 realizes that, look, I am bigger than 15. Since 18 is bigger than 15 and the elements to the left of 18 are already sorted. So 18 is still definitely bigger than everything else also because 15 itself is the largest element in this part to the left of 18. So no other comparison is required. One comparison between 15 and 18 lets us conclude that 18 should be present here. Because comparing 18 with something which is even smaller than 15 will not lead to any swaps. Is that correct? Or is that understood? So I'll say it once again. 18 is compared with 15 and it is realized, the algorithm realizes that 15 is already smaller than 18. So 18 should not be swapped with 15. So 15 should rather remain to the left of 18. Now anything to the left of 15 is already smaller than 15 because this part was sorted at the beginning of this iteration. At the beginning of third iteration. So anything to the left of 15 was also smaller than 18. So there is no reason we have to do any more comparisons of 18 with the rest of the elements to the left of 15. So that is why one comparison is sufficient. Now what has happened? We have been given this input. Then the first iteration, 1 by itself is in sorted order. The second iteration, we are worried about this element. What should be its position among the first two elements? So it makes a comparison, so it doesn't happen. Third iteration makes a comparison. Sorry, this is second iteration, makes a comparison with the next one. It is the same. There is no swap required. So in every iteration, with one comparison only, we are able to conclude that no swap is required. So one comparison per iteration. How many iterations? N minus 1 iterations. So number of comparisons, N minus 1. So what is the complexity or running time? N minus 1 only, which is order n. That is the reason this is the answer. Fine. Okay, we'll move to the next one. I think we'll not require. I think we should be able to finish by 7:30. We're not going very slowly also. That is fine. Again on insertion sort, another question. So what operation does insertion sort use? Question 7. What operation does insertion sort use to move numbers from the unsorted section, that means this section, This is pivot, this section, and this is sorted section. Okay, from the unsorted section to the sorted section of the list. So you can look at this example. So we had to decide about 18. I mean, we had to sort of push it to the sorted section from the unsorted section in this iteration. So what are the operations we have done? It is easy to answer. If we have swapping, Ganesh is saying swapping, that is right. Vince is saying yes. Both Ganesh and Madhubalan are saying swapping. That is correct. This is what we have seen in the previous two questions. The only operation we are doing to make a decision about an element, to move it from the unsorted section to the sorted section, is swapping. So this is the answer. It's a direct answer. It's nothing to analyze more than this. Then let's move to the next one. This is question number 8. For the best case input, the running time of an insertion sort algorithm is what? This we already have seen in the previous. So this question is directly related to question number 6. So what is the smallest running time of insertion sort? This happens when we have an input, which is the best case input. Right, Madhubalan is saying linear, that is correct. As we have seen in the 6th question, Swati is saying linear, that is correct. Vishal, you are saying D, depends on the input. Okay, so it of course depends on the input, but we are saying that the input is also specified. That is the best case input. Right, Vishal? So the best case input is the input for which the running time is the smallest. And we are considering that input. And for that input, the running time does not depend on the, I mean, if you have this input, or rather if you have 2, 2, 2, doesn't matter. If the numbers are all same, then whatever is the input, it is the best case input. But the running time is going to be linear, as we have seen in the 6th question. Linear means order n. Quadratic means order n squared. Okay. So n to the power k order means where k is a constant is polynomial time. So if we have a running time of order n to the power k, where k is a constant, then we say the running time is polynomial. What is binary running time? I don't know. So what is binary? Binary problem means I don't know. I haven't seen this word before. Anyway, I mean binary should mean 1, 2, but 2 running time in this context does not make sense to me. But if you have any doubts why the answer is linear, then you can raise your hand or you can ask me. Okay, so we shall move to the next question. Yes, Balaji, you are right. It is linear. So thanks for answering, all of you who have answered. Let's move to the next one. So this is the second last question of this session. The last question is going to be slightly tricky. So wait for the last question. Then let you read the question. So you have two sorted lists. One is of size M and the other is of size N. Okay. So you have two sorted arrays, let us say. Lists or arrays, does not matter. Plus, some numbers are there. One has N numbers and the other has m numbers. Okay, but they're sorted. Okay, so AI is smaller than AI plus 1, or rather AJ for all j greater than I. So these two are sorted arrays or lists, and you want to merge these two sorted arrays to obtain a sorted combined sorted list. Okay, so you want to apply mod sort on these two sorted lists to obtain a larger combined sorted list. So how many comparisons are needed? I already saw an answer. Somebody answered something. So Kevin is saying B. That is what he's saying. Any other answers? Balaji is also saying B. So we have obtained B as answer. Vishal is saying B. Anybody, any one of you who are saying B can give a small reason, some logic why you are saying B, that is max of n comma n. Oh, somebody has another answer. So somebody said C. Who is that? Right, Swati is saying C. Swati, you can probably give one or two sentences in favor of your answer. Madhu is saying D. So we have three answers. This was an interesting question. Nobody's saying A. So let's I don't know. So since you're not offering any reasons for your answer, let me try to offer some reason. So let's say we take some concrete examples. Okay. Okay, so I'm taking two concrete example. I mean, two arrays. Okay. So how about 1 and 5? This is one array, two elements, n is equal to 2, and this is the other array. So m is equal to 6. One element, one array has two elements, and the other array has 6 elements. So these two have to be merged. So how do you do that? So you look at the smallest element, compare them, and you have this result array which you want to get. So you realize that 1 is smaller than 2, so you push 1, or rather you place 1 in the result array. So you remove 1 from here. So then you have comparisons between 5 and 2. Then you realize that 2 is smaller than 5. So you place 2 here. You remove 2 from here. And you have compared between 3 and 5. So on. I mean, get 3, 4, and then at this point you have 6. These things are all gone. So at this point you realize that 5 is smaller than 6. So at this point you're left with only one partial array. The other array is already consumed within the result. So this one is already sorted. We just copy them into the result. Okay. Now that you have seen this example, would you like to give it another thought and revise your answer? is it mean of m comma n? So what was n? N was 2, m was 6. So we have we done only 2 comparisons? So 2 is mean of m comma n in this case. But we have done more than 2 comparisons, right? Isn't it? So 2 is probably not the right answer. The mean of m comma n is ruled out because of this counterexample that you are seeing. This is ruled out. Now we have 2 options. So some people are saying B, one person has said D. Those of you who are saying B, do you see any problems with your answer? Okay, so you're still with B. So let me write another counterexample to B. Take something small.
So in case of worst case, in each comparison, we are neglecting one number. So finally, one number will be left at loss. So obviously it should be, might be m plus n minus 1.
Okay. Okay. Thank you. Fine. So I'll repeat what you said. But why not A? That is the question. That's a prudent question. Why not A? Nobody has said A. Sujata is asking, and this is a valid question. It should be thought about. Why not A? So the question is it okay? So for now, let me argue that it is m plus n minus 1. If it is argued to be m plus n minus 1, in the worst case, I'm going to argue. Then of course, m into n will be ruled out because m plus n is much smaller than m into n, right? If you take two numbers, let's say 10 and 12, then m plus n is only 22, but m into n is 120. So if we argue that max we need m plus n minus 1, then m into n will not make sense. So that way we are going to rule this out. But it's a valid question to ask. For the worst case, yes. So what can happen? You have these two arrays. Okay, so you are building the output array. I'll take an example first. This is example, 2 arrays. So 1 compared to 2 in the output, we have 1. This is one comparison, remember. To get 1 in the output, we have made one comparison. We had to do one comparison to realize that 1 is in the output. We remove this. Second comparison is between 3 and 2. So we realize that 2 is less than 3. So 2 is in the output. So we remove 2. So I've already made 2 comparisons to get this far. Now comparison is between 3 and 4. So we realize that 3 is smaller than 4. So we have made one more comparison. 3 is removed. Now we make a comparison between 5 and 4. So 4 is removed and placed in the output array. Already we have made 4 comparisons. Remember, we have this partial output of size 4. By now we have already made 4 comparisons. Now we have the last comparison to make. So 5 turns out to be smaller than 6. And we remove 5. No other comparison is required because one array is already empty and the other array has only one element. So we put that element here. So except for the last element in the output array, this is output. This is the final sorted, combined sorted array. Except for the last element, for all other element, we had to do one comparison. Okay. The total number of elements was m plus n, that is c plus 3 in this case. So we in fact did m plus n minus 1. So question is whether the worst case could be even bad. So m plus n minus 1 is required. This example is telling us that there is an example. There are two arrays for which m plus n minus 1 is in fact required. So this and this are ruled out. Okay. So this now the doubt is whether m into n is a possibility. That is the doubt we have now. So the doubt is between A and D now. Okay. This is still a valid question that, okay, you have given me an example which takes m plus n minus 1 time. But maybe there is one more example. I haven't showed that there does not exist an example for which m into n is required. I haven't shown this. So we have to now argue that there cannot exist an example for which. Yes, what you call it?
Yeah, in case if you're going for m by in each iteration, the one element will be moved to the sorted array. So obviously it may not require m cross n.
Okay, fine.
Because under each comparison we are neglecting one number, right?
In each comparison, we're neglecting one number. So are
So
you
obviously
using
one number will be moved to the sorted array. So obviously, so in case we don't need the m cross n number of comparisons in this any of the case.
Thank you. I think you're not using a microphone. I mean this earphone. So if you use a earphone, maybe I will not get that echo. Or are you already using an earphone?
Now I will change to the earphone.
Okay, thanks a lot. Hey, these things are troubles we cannot predict. I mean, it should not have happened, but I don't know. Maybe the earphone will fix it. I don't know. I'm just guessing. So yeah, so what he said is correct, but I'll rephrase what he said. So what he said is that, look, you have these two arrays. One array having n numbers and the other array having m numbers. And we are targeting to obtain an output array containing m plus n numbers in the sorted order. Okay, that is our target. That is our target. So we want to obtain this array, which is containing all the elements in these two arrays, but in sorted order. So to fill this array, at most one comparison will be required per element. That's what his argument is. So his argument is that you are comparing, whenever you are making a comparison between one number in one list and the other number in the other list, you are populating at least one number, or rather exactly one number in the output list. So by the time you have made m plus n minus 1 comparisons, you must have filled this output array till the second last element, which is the m plus n minus 1th element, isn't it? So now you are left with only one element to be filled in the output array. And also, since you have already pushed or placed n plus n minus 1 elements out of these two, then the number of elements left in the union of these two arrays is also exactly one. So one guy that is left will come here. So that way, by the time you have made m plus n minus 1 comparisons, you would have filled the output array fully. So there is no way we can make more comparisons. Is that correct? Is that understood? right? So interesting enough. So you can practice questions like this. This is the last question of the day. It is the trickiest one. And then we will conclude. So this is last question of the day. So this is a recurrence. We've seen recurrences. What is a recurrence? A recurrence writes a function in terms of the same function, but with a smaller input. I would say a smaller parameter. So recurrences are generally written for running times of algorithms so that we can analyze that. What is the running time? So in many cases, we solve a problem by dividing it into subproblems. So smaller problem. One small problem, we divide it into two subproblems or rather multiple subproblems, and we solve these two. And then we merge the solution to get the solution to the original problem. That is a very common pattern of algorithm design. So if we have access to the running time of the subproblems and the running time to merge the solutions to multiple subproblems, then adding them together, we are able to calculate the running time of the original problem. I mean, running time of the algorithm applied to the original problem, to be precise. So that is the reason we need recurrences. That is the reason it is necessary to be able to solve recurrences. So here is a recurrence. That is a function Tn is expressed in terms of a smaller function plus some constant. And the question is, what is the asymptotic, type of this function? I mean, in the asymptotic sense, Tn would be equal to which of these four? Okay. So, I mean, it's a tricky recurrence to solve. So if you haven't solved recurrences, I do not expect you to be able to solve it. But if you have solved recurrences before, then you can give it a thought for a minute. We have an answer. Madhubalan is saying A. Why is that A? Okay, for some reason, I'm not able to hear you. Not audible. You can see that you unmuted yourself. Maybe just remove the earphones. So I'll not speak when you speak.
Speak. Can you hear me? No.
Yes.
Yes. Yeah. Just no idea. Just I thought that in case if you put the log of n, obviously you get that 1/2 of log of n, and it become quite linear. So I don't have exact idea. Just I thought that.
Okay. Thank you.
Okay. Thank you.
Okay. Okay. So I'll give you some. I'll give you some intuition behind how you can make guesses. If you have a question like this and you don't know how to solve it exactly, then one intelligent thing would be to just make guesses. Okay. So what is happening? So there is log n is also an answer to a recurrence, but that is a different recurrence. Okay. So consider this recurrence. Okay. So this is another recurrence. So now if you want to solve this recurrence, so what happens is there is a problem of size n that you divide into, or rather I would say this way, that you have a problem. This size is n. Let's use a different color. So you have a problem. Its size is n. So what you managed to do, your algorithm managed to do, is divide or rather derive from this problem a smaller problem of size n by 2. Okay. So you had a n size problem. So you were able to sort of derive a smaller problem out of it, and in the process, you have incurred a running time of 1. Okay, so what has happened is we are going to count how much running time is consumed. So with one cost, you are able to, so your cost of 1, and additionally, you have been able to reduce the problem size. Now you have a smaller problem of size n by 2, and on that problem, you are asking that, okay, now that I have a smaller problem, how much running time will be required? Okay. Now you know that you have the recurrence is still true. So because the recurrence is true, so t n by 2 from the recurrence is t n by 2 by 2, that is n by 4 plus 1. So this is equivalent to, so this n by 2 size problem, you can work on it and you can incur a cost of 1, and further you can reduce its size to n by 4. That is what the recurrence is saying. This is the meaning of the recurrence, this recurrence. Okay. So slowly you are able to reduce the problem size. So in each step, essentially you're halving the problem size. So at some point, the problem size will become 1. Okay, so what is that point? So that is the point when you have done this partition halving business, let us say k times. So the problem size has become 2 to the power k after k iterations of this halving. So at that point, you are going to say that, okay, now my problem sizes have become 1. So 2 to the k is n, simplifying. So that means k is log n. So after log n such partitioning, the problem size will become 1 from n. So this is first level, second level. So this way there is a log nth level. At that point, we have one size problems, which are thought to be trivial problems and taking just constant time. So the runtime you're incurring at each level is 1. So you have log n levels. So the overall time you will require is log n plus some constant, which is order log n. So this recurrence as a solution, Tn is theta of log n. So what is big theta that we have seen? I won't be able to go deep into it. So for this recurrence, this is a solution. Is that understood?
Yes.
Great. Now that okay. Fine. So now that you understood how to solve a recurrence, which is an easy recurrence, now we have to meditate on solving this slightly tricky recurrence. So let's say you don't know anything more than this. Then what will be your guess? Is it theta log n or more than theta log n or less than theta log n? Let's just focus on whether the answer should be more than log n or less than log n.
Must be less than log n. So final expression must be n power 1 by 2 power k. So after that, I don't know. I don't have any idea.
Great. So the observation is that the expression, the solution cannot be more than log n, because what is happening? So observe that in this recurrence, we are able to get subproblems of size half of the original problem. Okay. And plus we're incurring a cost of 1. But in this recurrence, we are further reducing the problem size. root n is much smaller than n by 2, right? So let's say n is equal to 100. So n by 2 is only 50. But root n is 10. So in each iteration, you are getting much smaller subproblems to work on. So the time required on smaller subproblems will be smaller. So the number of levels here you have is log n. But the number of levels, if you go on reducing at this level, you are root n. So first time you get n to root n. Next time from root n, you get n to the 1/4. Then you get n to the 1/8. And so how fast you're making progress towards getting to subproblems of size 1. This is much faster than this, right? So number of levels cannot be more than log n, that is for sure. Now look at the answers. Log n is ruled out. N square log n, that is so much bigger than log n. So this is also ruled out. Log squared n, that is also ruled out, right? So n squared is more than n, right? So log square n is also more than log. So all these things we have ruled out immediately, even without knowing how to solve this recurrence. So we'll just go ahead with this solution. We'll say, wow, we have got a solution without solving it. Yeah.
Yeah, but I came to the point n to the power of 1 by 2 power of k is equal to 1 to the recurrence. Then how to solve it to log of n?
Right, I'll tell you now. But even if you don't do this calculation, you should be able to choose the right option. That was the point. Okay, so now we're going to solve it. We're going to solve recurrences. So we have about 15 minutes time. I'll do it in 5 minutes, I think. So T of n, just remember the recurrence. So T of n is T of root n plus 1. Okay, so I'll write it here. Let's do one thing. I'll copy the question again. We are going to solve this recurrence. So this is quite like what he is saying. It's not easy. So the way we did the analysis before, so you incur a cost of 1, your problem size is root n, right? So this is equivalent to saying that, okay, I'll incur another cost of 1, then my problem size is n to the 1/4. So root of root n, right? Root n, take another root. This is n to the power half to the half, that is n to the 1/4. That's what I've written. Nothing fancy. That's all. 1, cost of 1, another cost of 1. Then what will happen? We have a smaller subproblem. How much? N to the 1/4 root over, that is n to the 1/4 to the 1/2, that is n to the power 1/8. Like that will go, right? So at some point we'll hit problem size equal to 1. At that point, let us say we have done k iterations. Okay, so then we would have 1 is equal to n to the 1 by 2 to the k. Yeah. So now what shall we do? So what is the solution to this equation? So 1 is what? 1 is n to the power 0, isn't it? Is that right? So what does that mean? 1 by 2k is 0. So k has to be really large. That is problematic. So if 1 by 2k has to be 0, then k has to be extremely large. But we don't want that. So we are stuck, isn't it? So we're able to go till there, Madhu?
Yes, sir.
Okay, so what shall we do?
Hereafter, I don't have any idea. That's it.
Okay, fine. Okay, fine. Okay, you can mute yourself. So now we are stuck. So when we are stuck, so we do something different. So in mathematics and life, we have to find different ways. and we are stuck. So let's do one thing. So we'll do a transformation. Just a second. Right. So we'll do a substitution. Okay. So observe that we want to get log n. So we know this is the answer. We are doing reverse engineering. We want to get log n. So we want to have some log somewhere. So okay. So we are going to write a new variable. Use a different color. We are going to write a new variable m, and we'll set, why is it black? We'll set m to be log n. Okay. So now what does this mean? This means that n is 2 to the power m. So we have base of log as 2. So this is log to the base 2. So after this transformation, we will be in business. So this is the substitution we have made. Now what is the recurrence? So t of, so n is what? 2 to the power m. What is root over n? So root over n is 2 to the power m into half, that is 2 to the power m by 2. Yeah, nothing fancy. We're just writing this recurrence. We're just writing this recurrence with this transformation in mind. This is what this is called a substitution. We're allowed to do this. We're just introducing a new variable m. Okay. So now we have a different form of the recurrence, which is sort of easy to handle. Okay. So are you with me this far?
Yes, sir.
Okay, great. Okay, great. So now we'll do another substitution. So we'll say that okay, let's do one thing. We'll introduce one more function, s of m. So we'll say that s of m is t of 2 to the m. So now with this transformation, so this is another substitution. We can do that. We're allowed to do it. We are going to write t of 2 to the m as s of m. And so that means t of 2 to the m by 2 is s of m by 2 plus 1. So what does it remind you? This recurrence reminds you of what?
The previous merge shot.
Great. So we are done. So we know how to solve this. So we know that solution to this thing is theta log m, isn't it? So this is the same thing. I've done this before. This is the recurrence. So instead of t, we have s, isn't it?
Okay, got it. Thank you.
Okay, so now we will replace m. Now we'll replace m by, what is m? Log of m. So what is s of m? S of m is t to the power 2m. Okay. So what is 2 of m? 2 to the m. 2 to the power n is n. So that means t of n is this. Okay. So we are done. That is the answer. Is that fine?
Yes, great. Thank you.
Okay. Okay. So I hope everybody else has understood it. So I think I am done for today. So I plan to discuss 10 questions. We're done for today. We have 8 minutes left. I am here. If you have any questions, you can ask me. If you have any doubts, any suggestions, anything for the next sessions, you can tell me. We can talk. Otherwise, we'll close it. Okay, so we'll meet next time. So next time again on Tuesday on 6th. Next to next week, that is on 13th, I won't be available most likely, but I'll update it. So you'll get a notification on the course page. But to make up for that class, we'll have an alternate problem solving session on some other day. But next week, definitely I'm going to be there. Okay. All right, fine. Then I'll say you good night. Enjoy.